All right, hello there, calculus folks. This is lesson 6_8. It's the last in our lessons on our first chapter in vectors, and this may be one of the weirdest learning experiences that you will ever go through. I don't know. Certainly, it's one of my weirdest teaching experiences. Um, I'll tell you why in a moment, but um, basically, what we're going to be doing today is we're going to be constructing a three-dimensional model. And of course, with the flipped classroom, I kind of have to instruct you to do that. And I'm going to try and do that using my webcam here. Hello. See, here I am. Hello. In order to do this, you're going to need a few things that I listed there. You need um, two pieces of paper. One is this piece of paper, which I think I've given to you in class. This is going to become a three-dimensional model. The other thing you're going to want is the notes from this lesson, either that you're going to fill out as we go through, or already filled out, and that will have been posted on the Facebook group. You will also need ruler and two sticky notes. Okay, I probably will give you the sticky notes in class beforehand. And this is what's going to make it weird. Look at, there I am. Kind of not looking there. Now I'm looking in the camera. Anyway, and I'm going to try and make these videos short so when I goof one up that I can stop and not have to go back from scratch. So we're starting off. The warm-up is on the bolded page. I'll call it the bolded page. It's got thick lettering, and you're asked to recall some stuff about in R2, which is the plane, two-dimensional space. The following can be stated about vectors x and y. So these two, well, they're parallel, right? So that's one thing we're going to say. I've got a lot of this stuff written already, so I'm going to go pretty fast. You can always pause. We say that they're collinear because they'll fit on the same line. They're parallel. They're scalar multiples of each other, right? So that means to get one, I can just multiply by some scalar, and that's a little more mathematical. X equals ky for some k that's a member of the real numbers. Uh, what was less familiar, perhaps, is this idea of a linear combination. We did talk about this, but this idea of, you know, I can find an infinite number of values of a and b such that when I multiply by this and add a scalar multiple of y, that I can get back to 0 without a and b both being 0. Notice that if a and b are both 0, then it's trivially that linear combination is equal to 0. But for instance, this one, it looks like if I had a y, so b was 1, and x was 2, or a was 2, y plus 2x's, that I'd get back to the 0 vector, and then a and b are not both 0. So add that to that first page. And then next thing, we're going to go back to the notes. Here's the notes, and I'm going to read this introductory part. It says, normally we think of I and j, which are the unit vectors along the x and y axis respectively, as the spanning set for R2. But they aren't the only spanning vectors. Two vectors, u and v, form a spanning set for R2 if every vector in R2 can be written as a linear combination of u and v. Well, what the heck does that mean? Well, that's what we're up against today, and we're going to actually extend our thinking to 3 dimensions. So let me go through this. This is back on your page, back in the corner. So in R2, if u and v are non-collinear, and see, here we go. On this page, we see u and v. Well, they're not collinear, right? They're not parallel. So it doesn't fit the case of x and y up here. We're talking about a different thing, u and v. And so what does it mean? It means they're not parallel. Well, that's clear. They're not scalar multiples of each other. So I can't get one by multiplying the other by some scalar multiple. which also means that any linear combination is equal to 0 only if A equals B equals 0. So this idea here is no matter what I want to do, how many ever times I multiply U by any scalar multiple and V by any scalar multiple, I can go out that many ways that I'm never going to get back to 0 unless those scalar multiples are both 0. Okay? And so this also means, and I'm going to skip to my next page here because this is getting close to the important part of today's stuff. Any other vector in R2 can be written as a linear combination of U and V. So this is the page, and now I can actually talk about it without getting my finger in the way. That any vector that I drew on this page, wherever it happens to be, and don't mess up your notes here, but say this one here, any old vector that I wrote, and it could be anywhere, because remember, vectors don't really have a position that's important. We can put them anywhere we want to. That wherever this is on the plane, then U and V are spanning set vectors if I can take some scalar multiple of V and some scalar multiple of U, something like that, add them together, and I get my answer vector. Okay? And we're actually going to do this for W. If I can do that for all vectors, then we call it U and V spanning vectors for their plane. Okay, before we get to the rest, I'm going to pause the video, stop the video, and give you a little breather and give me a little breather.